Now I want to introduce a topic that may strike fear into your heart, and that has to do with binary. Now let me explain a little bit about my background with mathematics, just to sort of set you at ease. I was in remedial math many times. I remember one time I was actually in Mrs. Pelletia's sort of remedial math. She didn't like me, I didn't like her, and I didn't like math. So trust me when I say if I can learn and understand binary and use it frequently, you have a great chance of being able to do it. But one of the things I want you to understand is that when it comes to computer networking, binary is king. In fact, on a blog entry that I wrote a number of years ago, I said binary are the keys to the kingdom. When you understand how the ones and zeros work, everything else in networking and computing makes sense. So if there is a secret magic bullet, this is the closest that you're going to get to it. Understanding binary. So let's just do just sort of a general overview of how this works, and we'll kind of do it step by step so that it actually makes sense based on things you're already familiar with. First, as human beings, we look at things in terms of tens because we have 10 fingers and toes. And from the earliest days, as you may remember in school, you may have even counted on your fingers. And that's how human beings tend to think in terms of tens. It's called decimal. However, computers are different. They can only process in groups of two. And this is one of the things to understand. The reason why it can only think in terms of two is because there are only two possible states of an electrical circuit, which actually makes up a computer. It's either on or off. On is 1, its current is flowing, like when you put a light switch on, as you see pictured here. And off is when current is not flowing, or 0. So a circuit can either be on or off, 1 or 0. And that's pretty much the only reason that computers think in terms of 2 is because of the state of the electrical circuit. Dimmer switches don't count, by the way, because a dimmer switch, even if there's a little power, it's still on. Now let me just give you an example. In math class, we have what's called the powers of 10. In this case, the number 10 million. To break this down, first you have the ones place. Remember, anything to the 0 power is 1. Well, 10 to the 0 is 1. It's the ones place. Anything that's in here is in the ones category. Then you have the tens place, which is basically just 10 times 1. So anything in here is going to be some multiple of 10. Then 10 to the second power, or hundreds place, 10 times 10, it's going to be in that range. Then you have the thousands place, 10 times 10 times 10, 10 to the third power. Then you have the 10,000s place, the 10 to the fourth power, 10 times 10 times 10 times 10. Then the 100,000s place, 10 to the fifth, 10 times 10 times 10 times 10 times 10. Then you have the millions place, which wouldn't we all like to make $1 million? You have 10 to the sixth power, 10 times 10 times 10 times 10 times 10 times 10. Everything in the millions category, aside from being highly taxed, is going to be in the millions. Then you have the 10 millions place, 10 to the seventh power, 10 times 10 times 10 times 10 times 10 times 10 times 10. The powers of 10. This is how this works. This is basic math. This is how we think. Mrs. Pelletier would be proud. So, if we want to break down the number 412,000, you notice you have 2 in the thousands place, so that's 2,000. You have 1 in the 10,000s place, which is 10,000. And then you have 4 in the 100,000s place. So you can think of this number as 400,000 plus 10,000 plus 2,000 is 412,000, based on powers of 10. With this number, 1,421,331, you have 1 times 1 in the ones place. You have 3 times 10, which is 30, in the tens place. 3 times 100, which is 300, in the hundreds place. 1 in the thousands place, so it's 1,000. 2 in the 10,000s place, which is 20,000. 4 in the 100,000s place, which is 400,000, and 1 in the 1 million's place. So 1 million plus 400,000 plus 20,000 plus 1,000 plus 300 plus 30 plus 1. That's the way the numbers break out in terms of the powers of 10. We think in powers of 10 because everything is multiples of 10. Computers have no clue. And it's not just enough to tell the computer, well, just multiply everything by 5 and then it'll all make sense. Still doesn't work because of the electrical state of the circuit being on or off. It has to be a 1 or a 0, on or off. So let's do an example. So just as we went over the powers of 10, let's now talk about binary, or the powers of 2. Everything is going to be in multiples of 2. So again, remember, 2 to the 0 power, anything to the 0 power is 1. So that's where we start. That's the ones place. Then you have the twos place, 2 to the first power, which is just 2. Then you have the fours place. Notice here, it's multiplying every time you move over. So you have the ones place, the twos place, the fours place, 2 times 2. Then you have the eights place, which is 2 times 2 times 2. 2 to the third power is 8. Then you have the 16s place. 2 times 2 times 2 times 2. Very similar to what we did in the powers of 10, but we're doing it with 2's now. Then you have the 32's place. 2 to the fifth power, 2 times 2 times 2 times 2 times 2. Then you have the 64's place. Again, you're seeing another doubling. 2 times 2 times 2 times 2 times 2 times 2, be the number 64. Then you have the 128's place. 2 to the seventh power, 2 times 2 times 2 times 2 times 2 times 2 times 2, which would be the number 128. Incidentally, this will be important later when we deal with subnetting. So the powers of 2, critically important, because everything you do will be related to the powers of 2. So let's put it all together. Let's actually make sense of how this works. So the number in binary here, 1 1 0 0 0 0 0 0. You look at that and go, okay, wonderful. What does it mean? Remember, 1 is on and 0 is off. So in this case, you have 1 in the 128's place, 1 in the 64's place, and then off everywhere else. So 2 1s and a whole bunch of zeros. There's 1 in the 128's column. So 1 times 128 is 128. Pretty much, if there's a 1 there, you count it. If there's a 0 there, you don't. So we've got 128. Then you have a 64, because there's 1 in the 64's place. Now, what do all these zeros mean? It's all zeros. Now, add the 128 to the 64, and you get the decimal 192. This is how binary works. Now, let's do another example, one that's a little smaller. 0 0 0 1 0 1 1 0. So there's 1 in the 16's place, there's 1 in the 4's place, there's 1 in the 2's place, and there's 0 everywhere else. Remember, zeros you don't count because they're off. So off and on. The 3 leading zeros, you leave at 0. Because there's a 1 in the 16's place, that's the number 16. Obviously a 0 in the 8's place, but then because there's 1 in the 4's place, that becomes the number 4. There's a 1 in the 2's place, that becomes the number 2. And obviously a 0, you add them all together and you get 22. This is the binary representation of the decimal number 22. When you think about it in terms of the powers of 2, it actually becomes very simple and easy to calculate. Certainly a lot less scary. Let's do a few more. So now we have 0 1 0 0 0 1 1 0. Remember, ons and offs. So there's a 0 in the 128's place, so we don't count it, but there's a 1 in the 64's place, that's the number 64. The next one is in the 4's place, so that's the number 4. And then you have 1 in the 2's place, so you add 64, 4, and 2 together and get 70. This is the representation of 70 in binary. Now, 1 1 0 0 1 0 0 0. Ons and offs, ones and zeros. So there's a 1 in the 128's place. That becomes 128. There's a 1 in the 64's place. You count that as 64. You skip down to the 8's place. There's 1 there, so you have an 8. So you take 128, 64, and 8, and you add them up to 200. It's the representation of 200. All these add up together. So let's see how quickly you can get this. Using the same process that we've been using. Remember, 1 times the place number. That's the number. Count that. Add up all the ones together. Ignore the zeros. Let's go. And it's 225. So we've kind of demystified binary. You figured out how the powers of 10 and the powers of 2 compare. Remember, the powers of 2 is how you're going to do all this. And how to be able, essentially, to convert binary to decimal just by using the place numbers. 1's place, 2's place, 4's place, and so forth. Well, another thing that's important to be able to do in networking, and certainly would be a part of your ICND exam, is to be able to convert decimal back to binary. And let's just give you an example of how this works. I jokingly called this the Reinhardt theorem because it's one way to be able to take what can be a very interesting and scary process and make it very simple. So let's think about how to convert the number 210 into binary. So this is the number we want to convert, 210. Write out your place numbers, 1, 2, 4, 8, 16, 32, 64, and 128. The first question to ask when trying to convert the number is you start with 128's place and you see if 210 can be subtracted by 128 and still be a positive number. And it can. Therefore, you subtract it and you're left with the number 82. Then move to the 64's place. Can 82 be subtracted by 64? Ding, ding, ding. You win again. Yes, it can. So you subtract that, and you have the number 18 left. Now move to the 32's place. Can 18 be subtracted by 32? No. So you ignore that one. You move on to the next one. Can 18 be subtracted by 16? Yes, it can. Now you have the number 2 left. Can 2 be subtracted by 8? No. Can 2 be subtracted by 4? No. Now, can 2 be subtracted by 2? Yes. And at this point, you're done. You're left with the number 0. Now, go back for every number that you were able to subtract, place the number 1. For any number that you were not able to subtract, put a 0. Or you can just say, where there was a yes, put a 1. Where there's a no, put a 0. And you end up with, and that's your binary number. 210 in binary is 110-10010. Very simple. Very easy. This is great stuff. So let's do that again, because remember, repetition is the price of learning. So number 47, smaller, less daunting, right? So let's look at the number we want to convert. Remember our powers of 2, and then we start with the 128's place. Can 47 be subtracted by 128? No, it cannot. Can 64? No, it cannot. 32? Yes, 32 can be subtracted from 47. So we subtract it and we're left with the number 15. Now, can 15 be subtracted by 16? No. Can 15 be subtracted by 8? Yes, it can. So we subtracted 15 from 8 and we end up with 7. Can 7 be subtracted by 4? And yes, it can. We're left with the number 3. Can 3 be subtracted by 2? Yes. Leaves the number 1. And can 1 be subtracted by 1? Yes, and we're left with 0. So we have now mapped out the entire number. So now let's go back. We have no, no, yes, no, yes, yes, yes. Remember? Zeros are no's, ones are yeses. So we have a 0, a 0, a 1, a 0, and the rest are all 1s. So 47 in binary is 0, 0, 1, 0, 1, 1, 1. Or you can suppress the leading zeros and just say it's 1, 0, 1, 1, 1. But easy to convert. So just some terms to be familiar with from this particular lesson. Decimal, or sometimes referred to as base 10, is a mathematical numbering system based on units of 10. And because we have 10 toes and fingers, it's the most familiar to us as human beings. Conversely, binary, or base 2, is a mathematical numbering system based on units of 2 and most familiar to computing machines because there are only 2 states of an electrical circuit, on or off. Thank you for your attention. It's very exciting stuff, and hopefully it really opened your eyes as to how to deal with binary.